once again. We are going to talk about stiffness reduction, the change of damping or the selection of damping, and also the response reduction and related omega factors and CR/CD factors that modify the response from the true response to the design level response, and see how they affect seismic and wind analysis. Actually, the focus today, I will keep it on seismic because wind is a different subject, which probably we will come back to in another talk. So let me see. Let's start once again with the fundamentals. I have already discussed the fundamentals previously, so I'm going to skip a few slides and you can look at those previous webinars to see 5 or 6 slides before this one. But this is the main equilibrium equation that governs the response of a structural system for earthquake loads and in fact general loads. So we have the external force, which could be coming from the ground motion generated by mass and acceleration, internal force generated by mass and acceleration, movement of the structure at the acceleration varying with time, damping of the structure once again multiplied by the velocity varying with time, and the stiffness of the structure multiplied by the displacement varying with time, and the nonlinear correction also varying with time. So these are the key components of the dynamic equilibrium of the structure at any given time t. And as you can see here, our structure is a general structure composed of the mass, stiffness, and damping stiffness matrices coming from the properties of the structure. And then the known here are these, and the unknowns are the displacement, velocities, and acceleration. Once we solve that, then we can solve for the internal forces and other response. So that's the general procedure we follow. Now, from this equation, actually, we can derive various methods of seismic analysis like modal analysis, the simplified equivalent static method, which we will discuss today a little bit. And then we can also look at the response spectrum, which we will also discuss today. And then we can also look at the pushover, which we will just also discuss slightly today. And then linear time history analysis, subset of the nonlinear time history analysis. So that's roughly the analysis procedures that can be followed. Now, obviously, doing all of that is great, and we have talked about this in both 2 webinars, one on performance-based, one on nonlinear analysis. But let's get back to, and we discussed the modal analysis last time. Let's get back to the structural design in the traditional way, code-based approaches. So if you look at the wind load and seismic load, in fact, seismic load effects, they are very different. Wind load and other loads, even live load and dead load, they are physically kind of applied on the structure. There's a number that you can see, and then you can quantify it, and then you can apply it onto the structure. Seismic demand, on the other hand, is generated by the structure because of the ground motion. So it's not an applied external force, it's a displacement which generates internal force, which then generates the demand and the corresponding forces in the member and so on. So it's totally opposite to each other in the way these 2 effects are generated. And that's one of the reasons that the design methods are also opposite. On the design and for the wind and for gravity loads, we normally design within the green range, which is the linear and elastic range just before yielding. Whereas for the seismic, we design beyond yielding. And we have looked at that chart, we have looked at many times on how that R factor, omega factor, and other come into play. And we are going to talk about the right-hand side and go into the a little bit more detail of R, omega, and the stiffness reduction and things like that, and how the right-hand side works. So before we go there, once again, gravity and loads and wind loads are very, very clear. We have a characteristic load, which is the actual load. We can call it service load, design load. Like, for example, design wind pressure, for example, or design live load, design dead load. We amplify them by a load factor, 1.6, 1.4. And then we calculate the capacity at the yield point, and then we reduce it by a capacity reduction factor, either gammas in Indian and Euro and VS codes, or by phi factors in ACI related codes. So basically we get them out. And for that we use the gross stiffness, normally the uncracked or the gross stiffness to do that. Whereas the cracked or after deformation or after yielding, the stiffness obviously reduces, and that's the reduced stiffness, the green line. So that's the basis for the gravity and wind load design. Low level wind load, high level wind load, is a different story, which we will discuss some other time. Earthquake, on the other hand, seismic effects is on the other hand, we reduce the load, not increase it. So we have the MCE level demand, we reduce it by 2/3 to go to the design basis of earthquake. From there, we reduce it by R to go to the design level. And that is the force level, which is supposed to correspond to yielding. And that's where we design, we compute without knowing what's going on. So this graph should be enough to do that. And from there, the displacements are checked against the CD factor. And these factors, CD and R factors, are given in the code for different structures, and they vary in there. But the real true response is the red line. And you can see here that the slope of that curve may be different, and that will correspond to the reduced stiffness because of the yielding and cracking and whatnot. And then you have the omega factor to account for various overstrengths present in the structure, which we will talk about today. And then the net reduction in the demand from design basis to the top of the true demand, which is a true reduction, of this the structure as a whole, which is less than R, by the factor of omega naught. So the R can range from as low as 1.5 to as high as 8. Omega can range from 1.5 to 3, and the stiffness reduction can range from 0.25 up to 1. So these are the typical ranges where these values can change, and we can have this whole shaded area, which is kind of an unknown. Depending upon the choice of the factors, we can be anywhere in between. The red line could be touching the dBE in cases where the R and omega are equal. So for the performance-based design, for the full nonlinear dynamic analysis, we can start with the MCE directly. We get the input of the ground motion at the MCE level, and then we let the structure decide where it's going to go by yielding, by all of that reductions. And then we calculate the demand at the given level of the displacement, corresponding to a particular performance level. It could be the collapse level, or it could be the service level. So we have a service level earthquake corresponding to service level evaluation, which is more or less elastic, linear, without much damage. And we have an MCE level, which will cause significant damage, so much so that the structure may have to be demolished at that point, but it still is prevented from failing. So that's the overall framework for performance-based design. So we go from one to the other because we can't always do this. Of course, performance-based design, if you do that, you can get the true demand from there. But if we can't, then we have to rely on the code-based factors. So looking at the full force displacement curve, that red one, it has many components, many things embedded there: the initial stiffness, the yield point, the strain hardening, ultimate strength, ductility limits, strength loss, and residual strength. So many things are embedded in that red curve for any component, or even for the whole structure. So this gives us the change of stiffness, with displacement. So as the displacement increases, the stiffness keeps changing, which is the slope of this red line. And then we have the loading, unloading from the typical, seismic demand. It goes up and down. It's an oscillatory motion. So we have the positive and negative loading, unloading, and increasing, decreasing demands. So we have the blue line, which is the hysteresis, and it has many loops. On each loading, unloading produces one loop, and then it can degrade the structure. It can reduce that. It can bring that red line even further down due to degradation of the cyclic loading. But this degradation includes the energy dissipation, which is the area under that loop for each cycle. And then that energy dissipation can lead to the equivalent damping or damping being increased with each cycle. So that's how the damping and stiffness will change over displacement and over cycles. So that's the basic sort of understanding of the mechanics behind the whole nonlinear dynamic analysis. So before I go into the details of that, let's look at some case studies and see how these factors affect the response of a typical building. I've taken two case study buildings. Dr. Pramin, my colleague, helped me to generate this part of the presentation. So first is a 50-story building, and we look at a building with the podium and with the tower. It's a kind of an idealized, but not too artificial. Many buildings are of this kind, tall buildings of this kind. We have a core in the center, and then we have a service area around that. So it's not completely abstract. So we take that building, 50-story building. We first do the gross analysis. That means we use the gross properties as computed from the gross member sections, columns, beams, and walls without any reduction. And we see how when we look at that. So that's the mode shapes of this building and the natural period. The first period along the weaker direction, 5 seconds. Second period along the stronger directions, 3.35, and the torsional 1.54. So from the previous webinar, we remember this is a symmetrical building, and we have the first two translation modes followed by a torsional mode. So it's pretty much okay with what we expect this to be. But what is important is the difference between first mode in the weak direction and the first mode in the strong direction. There's a significant difference, and that is coming from the layout of the building, and that is kind of intentional here. So if you look at that, you will see here that the modal participation mass ratios, which is a very important outcome of the modal analysis, is that how much mass is participating or moving in each mode. So the first mode is in the weak direction, which is the X in this case, 5 seconds and 45, 40, 48. The first mode is taking about 48 something percentage of the mass. And second one in the y direction also similar. So that means the first primary modes in both directions are taking roughly 50% of the mass, which means the higher modes will be very important. The next level of the modes will be taking about 20% roughly, and then another one, 10, and so on, until we reach the 90% at about 12, 15, 18 modes. So that's typical of a tall building of this kind, that you need about that many modes to accumulate the mass, all of the mass participating in the movement and to compute the forces. But you can see here that the first and the second mode in the two direction are rather different. And now we come to the next one. Okay, so this one now we bring in the response reduction into the equation. So as I was saying, that the modal participation ratio is very important until we get the 90%. Okay, and then we bring in the R, and in this case we have selected the building with the core wall and the frame, and its R is 6 and CD will be 5, and we will use that for the further analysis. And now we look at the response spectrum from which the forces will be generated by using ETABS in this case, and we define the response spectrum for this building, and we input these values over there, and then we generate the response. And we can see now here that there's 2 points marked on the response spectrum. The first one is the X direction, is the first mode at around roughly about 5 seconds something. And you can see here that the demand at that point is pretty low. And then the second mode on the other direction, the Y direction, which is the stronger direction because of the large shear wall, is about 3.5 seconds, 3.3 seconds, and we have a higher demand in this one. And then if you go further, you will see that the next 2 modes in the X and Y direction are much smaller in the natural period and with much higher demand. So as we are moving towards higher modes, even though their mass participation ratio will be less, maybe 20%, but their response coordinate is large. So their contribution will still be large. So even though we have 50% for the first modes, roughly, and 20% roughly for the second group of modes, their ordinates on the response spectrum are different, so their contribution will be still significant, and we can see that later. So this is what's happening now from this building response using the gross sections and with the R factor. Let's continue. And if you look at the now base shear, this is a very important. So what I'm showing you is the minimum global response that we should study. The first one should be the model, which we already did. Second one should be base shear. And the percentage of base shear is critical because this tells us whether it's realistic or not. So this base shear is roughly in the two direction, it's no longer equal. So that is very important to note here. Even if the same response spectrum, same building, two direction forces are different because of the glacial period is different and the response ordinate on the response spectrum are different. So you get larger force in the stronger direction, smaller force in the weaker direction, 5% to 7%. This is not too high for a tall building of this kind. This could be a good range, although sometimes it is limited to 3% by certain codes because, this is still because of the mass is very large. So 7% global response, what we've seen so far, and before we go on further. Now let's go back and include these reduced stiffness in these models according to the code. Now, you can see that we are going to incorporate now the green line in the analysis, which is the reduced stiffness, and the slope will increase. So we will have the green line to represent that reduced stiffness, matching more closely with the yield level stiffness. So how that is done is through the codes. And this is the ACI 318, 19 formulas. You have 3 formulas here, 3 groups of formulas here. Left-hand side is the general approach, it's constant numbers which you need to check. For the walls, there is a range for uncracked and cracked. If it's cracked, you need to come back and modify again. So you run it twice. And there is a general formula that you just use 0.5 IG. If you are lazy and don't want to do anything, then we can just go ahead with that. But then there is an alternate method, which is this one, which is very detailed. And this is not used a lot because it requires the knowledge of forces and reinforcement and everything, and which tries to estimate the cracking and the stiffness reduction more reliably, and it will vary from member to member. But it's very hard to compute and not often used in practice because it requires significant additional work to be done. But that is more realistic. Other assumptions are more approximate, but we will see that how much the effect this has. Okay, now after the gross versus we reduce the response, you can see here now that the natural period has increased from 5 seconds to roughly 7.5 seconds. First mode lengthened significantly from 5 seconds to 7.5 seconds, 2.5 second lengthening of the period because the stiffness is reduced, entire building, especially the core walls. And then we have the second mode, also same thing, reduced from 3 to 4 point something, and then the torsional mode as well. So we can see significant lengthening of the period by reducing the properties of the members from the gross to the cracked based on the codes. If you compare the model mass participation ratio, they will not change much. They did not change much because the mass hasn't changed, the distribution hasn't changed. So even though the initial period may have changed, but their participation factors haven't changed significantly. So they almost remain the same. But sometimes they can change if the structure is unsymmetrical. Sometimes unsymmetrical structures become symmetrical, and sometimes symmetrical structures become unsymmetrical after we apply the reduction factors, because if the structure is not symmetrical, their effect will not be symmetrical. So this has not changed much. Then we can now see the change in the base shear, and you can see here that there's a reduction of about 18% on both directions due to using the cracked section. So this is quite significant that the estimated base shear due to earthquake of the same response spectrum and same structure is now calculated to be 18% less than the one with the cross section. And so depending on how we look at it, it could be good or could be bad. But you will see later that 18% is not a big number because we're talking about an R reduction of almost 6 times 600% or even 800%. So within that 18% is not a very big number. So the stiffness reduction factors, they do affect, but their effect is not proportional to the R factor variation, although this is added on top of the R. So now you can see here that for a building of this kind, which is tall and the period is already pretty long at the bottom of the flat portion of the response spectrum, the change in the period does not change significantly. And then we can see 18% in this case. And this is typical of a tall building of this kind, that even the cracked and uncracked section, or even if you include the solid structure inflection or don't, they do not affect significantly because the building period is already too long and is not affected much by stiffness change. And same thing will happen with story shear and moment comparison. They also reduce in the similar manner, same amount. And then we can continue to see the drift and the displacement in the same way. So it's consistent that the stiffness reduction will increase the displacement, increase the drift, and reduce the drift and displacement because the demand is reduced. Now coming back to this curve that I showed you earlier, and we now can see that there is a R there and there's an omega there in the ASC 722. And then we have already discussed last time also that the effect of the R is to reduce the response and the omega is to increase it. And these two are kind of working together to ensure a reliable estimation of the final force for which we should design the structure. And we will we'll go into more detail of this one now. So now if you look at the base shear for including and not including omega and R, you can see the difference. So if you start with the R equal to 1, omega equal to 1, which is the blue, and then include the R equal to 6, omega 3 for this structure, you will get very clearly, very simply, 2 times reduction or half of the force, because R divided by omega is 2. So the net reduction is only R divided by 3. 6 by 3 is equal to 2. So you get a reduction of 2. It's a very simple math, nothing complicated about that. So basically, the net reduction we will get at the top of that curve will be 2 times from the dB level, force level. Now, typically, the normal members will be designed for divided by R, and critical members and critical actions will be designed by the low force level divided by R, amplified by omega. Let's move on to another building now, a 10-story building, which is kind of on the other end of the spectrum, and see what happens. So for this building, we have maintained the core, although the core may not be as big as this one, but for comparison, we just maintained it in this building and see what happens here. And we continue, and we can see here that the increase from the uncracked to cracked is, natural period is still increasing, not at the same level at this one, but there's an increase from 0.48 to 0.776, and then similarly. So natural period is increasing from the uncracked to cracked, similarly as we observed in the 50-story building. And then the modal participation factors did not change, as we expect, much between the uncracked and the cracked section. And they are mostly, you can see, very high percentage is in the first modes now. It's not like the previous one. Major portion of the structure is is participating in the first mode, almost 70-75% in this case. But the point to note is that now we are on the descending sort of level, branch of the response spectrum. So any change, any small change in the natural period will result in a large drop in the response ordinate on the left-hand side. And so which means that even though we change the natural period a little bit, but the drop in the expected response will be significant. And that is very typical of the buildings with smaller natural period. So they are very sensitive to stiffness changes, whereas the building on the longer periods are not so sensitive to stiffness changes because the response is nearly flat. But here we can clearly see that there's going to be a major change, and we have to be careful with the selection of these numbers. And you can see here that the drop is significant between the cracked and uncracked. And let's compare now the two buildings, the tall building and the medium or low-rise building, tall building on the left-hand side and the short building on the right-hand side. And if you can see, the reduction in the first one is about 18%, and the second one is about 30, 38, 35%. So it's significant difference between a tall building and a short building, between the uncracked and cracked models, which means that now it's something to be concerned what kind of factors we use because we don't want to underestimate the demand also. So that's, and a building with 5-story, 6-story, it will be even more sensitive, just in the short range of the spectrum. Okay, so that was about the stiffness reduction, one part of the equation. Let's go to the second one, which is the damping. Now, I will only do this for the 10-story building because the response spectrum for the 50-story is too flat to observe anything. So let's look at that. So that is the response spectrum generated for different damping ratios of the critical damping. 2% of the critical damping, that is typically the case for a very new building or a steel building, very new concrete building, uncracked, or a steel building. You will have roughly 2 to 2.5% damping as the starting point. 5% is the code-specified damping, normally for concrete building used, especially the low-rise buildings for the design purposes. And then 10%, 15% damping happens as the structure deforms and cracks and degrades. And like I showed you earlier, we have the cyclic, energy dissipation. The damping keeps increasing, so it can go up to 15%, even 20% or more. So as the damping increases, the demand ordinate on the response spectrum from this one starts to reduce. And you can see here for the 10-story building, with a period of 0.76, you can clearly observe the drop of the demand for each damping change. So let's see how much is that. So from 2% to 15%, there's a drop of 40%, which is once again significant. This is again quite significant in the sense that even though the R factor is large, but this is on top of that because we apply R after including the damping ratio and after including the stiffness modifiers. So this is a factor on top of the R that we use. So this demand, this choice of the damping is quite critical. In fact, the building that collapsed in Bangkok earthquake, some people are postulating that because the building was under construction, was completely new, the damping at that point could have been as low as 2%, and that could have increased the demand significantly compared to the 5% or damping used in the design. So that could be one of the factors that contributed to large base shear or large story shear being generated in that way, large forces being generated. So once again, selection of the damping is important, especially for the buildings which are in the short period range. And the choice of the stiffness reduction is important, especially for the building in the short period range, and less important for buildings, tall buildings, which are in the longer period range. So often these problems become more significant for people working on smaller buildings than the tall buildings. And this is, again, you can see the corresponding reduction in story shear. You can see the corresponding reduction in the story drift and moments and all. So it's very consistent. It's a kind of a linear problem. So it's just going like that. It's a linear analysis. So there's nothing different about that. Okay. Now let's conclude the two things together. And I'm showing you two different response spectrum. So you can also see how this is affected by the response spectrum shape. The blue line is the Manila response spectrum, typical, similar to the ASC, and the red one is this very special Bangkok response spectrum because of the basin effects and all. It peaks at 2 seconds rather than at 0.1 or 0.2 second like most response spectrum. So the effect of in this particular case for Bangkok, for example, the effect of the change of damping and the stiffness in buildings up to 20-story will be negligible because the response spectrum is nearly flat. And this is so different from Manila, where that region will be highly sensitive. So it's not just the building natural period, but also we need to see where the building is located and what is the response spectrum look like for that region to see which part is critical, which is not. And if I plotted the change in the stiffness and the change of damping for a building, 10-story building in Bangkok, you will see no difference. In fact, you will see slight increase on the contrary, rather than the reduction. But in the range from 20 to 30-story building, 2 to 3, there's a significant drop, and then it flattens again. So that's the important observation for both. So the reduced stiffness typically will lengthen the period and typically will reduce the demand. And the damping increase will bring down the ordinate of the response spectrum and also reduce the demand typically. But like you can see, it's not always true. We have to be careful about the response spectrum of the particular site. So we cannot use general response spectrum everywhere. We have to be very sensitive to trying to get the local response spectrum wherever possible, because the two interact. So both tend to increase the seismic, reduce the seismic band, tend to, I said not always, tend to. Typical reduction can be between 10 to 60%, and in some cases in Bangkok, it could actually increase slightly. So that's roughly the overall summary of the stiffness reduction and damping change. Let's come down now to R and omega and CD. So coming back to that figure, you can see here that R is the reduction from the design basis earthquake down to the design level. And this value is used for design of ordinary members like beams and columns, which are not critical, especially for bending and ductile behavior. We magnify that demand by omega naught to reach to the expected true demand for critical members like collectors of a diaphragm, shear walls, and other like transfer girders and so on, which are very critical for the safety of the buildings. We will have omega naught. This omega naught has not always been there. There was no concept of omega naught before 1977 codes in ASC. It only came after that, and gradually it has been sort of improving, and ACI took it in 2011. So 2020 or 2002 is where ASC introduced the omegas, and somewhere after that, ACI and other codes start to modify their methods to account for this observed increase. So both omega and R are opposite side of the same coin. One is trying to reduce the demand, elastic demand, to the design level. Another one is amplifying the demand to account for the real capacity because of so many factors. So both of them have two subcomponents, which I will just show in the next slide. So they're both very similar to each other, and sometimes they both can be equal, bringing the demand back to the elastic demand. So for R, we have three components coming from ductility, overstrength, and also from the period shift and damping effects and other. So some part of that is included in the R, some part we add externally as well. So basically it's observed, this is done from research, from testing, and I will show you one case where you can determine the R through analysis, roughly. And omega naught also has three components, one coming from material overstrength, because the actual strength of the material or expected strength is typically higher than the design strength through the observations you might have also seen. The steel, for example, typically is 25% to 30% higher than the design strength. So that really changes the actual yield capacity compared to the design yield capacity. Concrete, also, if it is delivered by the factories or the concrete suppliers, they typically deliver concrete higher than the ordered because they don't want it to be rejected. This is based on the sampling. So it's typically 30% more strength than the one ordered, once again increasing the actual strength on this in the structure, and structure also gains strength over time. Then we have the design over strength, because the actual sizes cannot be exactly the same. Sometimes the architect wants a bigger size. Sometimes you have members which are present without their need to be there. Redundancy, not all members can be optimized. You group them together, you design one beam and use it to 10 locations. 1 location it's okay, 10 location it's over design. So all over design components contribute to the over strength factor for the actual true demand to be higher than the computed yield demand from the design. So that's the reason we have the omega naught. And you can include these omegas and R's and others through scaling factors in ETABS. We will discuss that some other time in more detail. Let me go back to a very simple structure to demonstrate to you how this R factor roughly can actually be computed. And so this is a simple, very simple frame. There's no real redundancy. There's nothing other than that. So it's a rather pure structure that we have 2 columns, 1 beam. And if you look at that, so if you apply the force on this one using an elastic analysis, very simple frame analysis, and plot the force, you will get 2 plots. One is if you use the gross section, another one if you use the cracked section. So you can clearly see the change of the stiffness, the drop of the stiffness from the gross to the cracked using the code specified cracking section. So we can see stiffness dropping significantly in this case. Very simple to see that, so that's clear. Next, go to the next one. But reality is that the column is not just a gross concrete. It has reinforcement there, it has confinement there, it has spacing being the same way. So this is the typical detail of that column. We generated that from ETABS detailing, and then you look at that there's a lot of things going on. So we need to incorporate that into the capacity. So we go back and we take that whole frame, once again taken from ETABS, and then we include the moment curvature, we include the capacity of the column, as well as the moment curvature of the column and beam, and then we base that on the moment curvature for the beam, and then we put this nonlinearity, which incorporates the material nonlinearity as well as the section nonlinearity computed from the actual provided reinforcement, and then we generate the hinges, and then we put it back into the model, and then we do a pushover. And once you do that, then you can see that we get the nonlinear capacity now, not the assumed one. So here we have 2 nonlinear capacities. One is without P delta, and the second one is with P delta. So you can see that nonlinearity is not just coming from cross-section or rotation or the hinge rotation, but also coming from the P delta effects. And so when you include that, the capacity drops significantly further. So nonlinearity has several components. In this frame, we can easily see, and R includes all of that. Actually, not necessarily, but includes most of that. So now you can see from here that we have several graphs. Gross response, cracked response, nonlinear response without P delta, and with P delta, and large displacement. So we have several analyses that we could do on this frame using SAP or ETABS. One of my colleague Ashish did that a year ago. And then you can see now, so the important thing to note here is the displacement versus force values. So if you put the service level displacement, let's say 0.5% drift, which is typical for a service level, you get a force factor, let's say of 1. Whatever force that is, we call that as 1, which is just before yielding. If I increase that to the 2% drift, which is the design maximum level drift, you get a force level of about 3. And then if you increase that further to a 4% drift, which is roughly the MCE level for a very well-detailed frame and all, you get the force factor of what, 8. This is corresponding now to the omega, to the R, and to the MCE, and to the DBE level. So this is how we could roughly generate these factors for an idealized simple frame. But real buildings are far more complicated, so many members, so many yielding. The yielding doesn't happen at the same time. It starts one place, then it progresses, so the curve keeps on going up. So that's why these factors are based on a lot of research, a lot of testing. So both R and omega, and I remember in the initial ASC code, there were about 3-4 structural systems. Now there are about 25-30 structural systems there, because every time a new research comes in, more factors are added. into that table to make it more refined and more relevant. Let me talk about the last part of the presentation. It is the higher modes and R. R, in general, has been derived based on most of the studies on frames which have a first predominant period. But tall buildings, on the other hand, have higher modes which contribute significantly. As you can see from this graph here, the first mode, this is a moment graph for various modes. The first mode, you can see the moment is pretty straightforward, and then you get the true demand, and then from that, you get the elastic demand, which is, and then when you divide it by R, it comes to the red one, and that is when you divide it by R, you will get the green one, and the red is true demand, and somewhere in between, that's what we expect. A little bit more, so that's the omega factor between the green and the red. And that's what you will get for the first mode, which looks pretty good compared to the code. But for the higher modes, this is not this case. Now the difference is much larger between true and true. The true demand is getting closer to the elastic demand, which means there's not much reduction, and so on. And in some case, the true demand can even be larger than the elastic demand. And this is for the moment. But the moment, please note that the moment is not on the same scale. The first moment is plotted, the first mode moment is 10 raised to power 8, the next one is 10 raised to power 9, next one is 8, so it's one order difference. So the effect of the higher mode on moment is there, but when you add them together, it's less. Shear, on the other hand, is a different story. These graphs are, the three graphs are on the same scale. So now you can see clearly that the first mode reduction is similar to what we observe in moment. So the true demand lies closer to the demand obtained from elastic divided by R, green line, and then magnified by omega. But the higher modes are, the true demand is very close to elastic mode. So there is no yielding, there is no reduction. And the third mode, almost none. And in some case, it is above. And this is the most important observation from the studies carried out on tall buildings, modal separation and modal analysis, that the yielding only happens in the first modes in the traditional way. So the R is really applicable to the demand for the first mode. And higher modes should not be reduced by the same R factor. So now there are many research, especially in Thailand, the new code developed by colleagues, including Professor Penang here. It suggests differential R factor for different modes. And this is something now which is, obviously for very tall buildings, if you do the nonlinear analysis, true demand, you don't need to worry about that. But if you use R, then have to be clear, because the higher mode have a significant contribution in shear. And if you reduce it by R, you are going to miss the demand significantly. So that's the challenge using R with tall buildings, especially with the higher modes. So I wanted to talk about stiffness reduction. There are many slides here, but I'm going to skip that because we're almost close to the end of the 1 hour. So we will discuss these slides in another webinar. So can you just go on very fast? So we will talk about that the stiffness is built up, material to structure. Please go on, I think, and then how we have nonlinearity incorporating everywhere and how that is added up together. So I think we will come back to this on how the stiffness reduction happens. Please continue, next 7 slides. And moment curvature, how that can be used, and how the section cracks, and how the stiffness changes, and how we can calculate the difference between the gross stiffness and the reduced stiffness, and various types of stiffnesses, and so on. I think we can just skip all of that for now. I don't think I can cover it today. And how this is calculated, and how this is applied in ETABS, and how it is computed for gravity analysis and MC level, and so on. Please continue. And then we continue. And damping also, we will come back to damping, different types of damping, how it is computed, and how do we incorporate that in ETABS. I'm going to skip some of these slides, and probably Dr. Pramin will cover this part. And please continue. So we will talk about the energy and how the strain energy is accumulated from the section to the member, from material to the section to the member, and how we ultimately come to the total energy and how we limit the damping for different buildings, for different height, as I mentioned to you earlier, all of that stuff, different types of damping that we have. And then we will continue, please continue. And then how it is incorporated in ETAPs, all of these dampings, and then how the energy level is also cumulative from material to the structure, and how the damping also accumulates in the same way. So we have stiffness, ductility, and energy accumulating. So let me just come to the closing of the webinar today. All that slides that I showed you, we will discuss later, I think, because we need to spend time on that. So all I'm saying right now is, for today, we should observe that the left-hand side, what you see, is the true demand that we can obtain from the full nonlinear dynamic analysis. And we don't need any factors. We just get the demand at the service level earthquake and the MC level earthquake and check the performance. The codes, on the other hand, will try to get to the same story by using a combination of stiffness reduction, R and omega and CD. But attempt is to simulate that. The problem is that these factors vary a lot. So you don't know whether your choice of your factor is really correct for your particular structure or not. Even the R factor in two direction cannot be the same. We normally use the same. As you have seen, the building has two different systems or stiffnesses and yielding capability. So the R should not be the same in the two direction, and omega should not be the same in the two direction, and so on. So there's a lot of discussion on how these values, these numbers should be used carefully. Stiffness is the same thing. So we can conclude today that the simplified assumptions and design process procedures are sometimes needed and are justified, but we need to have a clear understanding of their origin, where they come from, why they're there, and their limitations and their impacts. And full nonlinear dynamic analysis, performance-based solutions is where the professional practice is moving on in the future. So with that, I think we can come to the end. Thank you so much.